Video, we're going to just quickly review Beer's law. So if you remember, Beer's law is on your formula sheet. It has this formula that looks like A equals ABC. It relates the amount of light absorbed by the solution, the absorbance, to the concentration, in this case C. So how I do that is A is this molar absorptivity. It's a constant. It's dependent on what the material is. It usually has units of molarity, -1 centimeters, -1. B is the path length. It's essentially how wide your test tube is. So a lot of times it might be like 1 centimeter. It's the path at which the light travels through the solution. So again, like how wide that test tube is. And C is your concentration in molarity. This is the Beer-Lampert law, also called Beer's law for short. So how do you measure absorbance? You do that with a spectrophotometer, which measures absorbance A or transmittance T. Absorbance is just the negative log of transmittance. So what you would do is you place your sample in a clean test tube and you would put it into your spectrophotometer, and the spectrophotometer passes through light through that container, through that cuvette or test tube, of a selected light of a selected wavelength. So you can set the wavelength to whatever you want, and it passes only that wavelength through, and then it measures the amount of light in that wavelength that was absorbed by your solution. So anytime you have a solution that has a color to it, you can relate your absorbance to concentration. And if you just think about like preparing a solution of Kool-Aid, the more solute that you add in, the darker and darker your color of your solution. So you can really relate absorbance or the color of that solution and how much light passes through to concentration. So since the solution that you're analyzing often contains other compounds in it than the one you want to analyze, you want to always compare your absorbance to a reference blank, or a blank we call it. So the reference blank should really contain everything in the sample except the substance being analyzed. So a lot of times we're looking at aqueous solutions, so a lot of times we're going to use distilled water as our reference blank. And if you remember when we were in the lab, these were the steps that we used to calibrate the spectrophotometer to our blank. So first you would set the wavelength to whatever you needed for the experiment to be run at. Sometimes there's a filter switch at the bottom that you want to set to the appropriate wavelength range as well. And what you would do is first, without anything in it, you would turn this left knob and you would adjust the machine to 0% transmittance, teaching it that when nothing's in it, there's no light passing through it, you want it to be at 0%. Then you would take a blank, you would prepare your blank, you'd fill up a test tube or your cuvette with distilled water, and you'd put it into the machine. You make sure the door's closed so no other light comes in, and then you would adjust the machine to 100% transmittance to teach it that the blank, which again it might be distilled water, or it might be distilled water and something else, depending what the thing that you're analyzing is, you're teaching that, okay, this is 100% transmittance when all this light is passing through this blank. And now you have calibrated the machine. You don't want to adjust any other these knobs any other time unless you're changing the wavelength. Anytime you change the wavelength, the machine needs to be recalibrated or re-zeroed. Okay, how do you figure out that wavelength? Is you want to analyze samples using the wavelength at which most of light is absorbed. So we call that the wavelength of maximum absorption. Sometimes you might see lambda max. So sometimes they might give you a graph of absorbance versus wavelength, and you would pick where you have the highest peak, the wavelength of maximum absorption. If you have other things in your sample aside from, let's say, water or something else that might be absorbing light a lot, you'd want to pick a place where you don't have interference as well. So when you're doing this, your cuvette and test tube, you should always inspect it for any scratches. You don't want to use something with scratches. You always want to place it in the same orientation, and you always want to wipe your cuvettes or test tube free of fingerprints. So if you remember, we would always wipe it before putting in. Why? Because any type of scratch or fingerprint can scatter or absorb light. So less light overall would end up reaching the detector. So it would seem as if the solution has absorbed more light than it should have. It would seem as if the solution's absorbing the light that actually the fingerprints or scratches are absorbing. So your measured absorbance will be higher, and your concentration would be higher than it should be if you're plugging into Beer's law. Okay, what does Beer's law tell us? So once you analyze your solutions, you can actually get what's called a calibration curve. So if you prepare solutions of known concentration and measure the absorbance, you can make this plot and you can get a best fit line to your plot essentially. And now if you make a solution where you don't know the concentration, you can just measure the absorbance, go across and drop down essentially like this, and figure out your concentration. Or you can get your best fit line and plug into the formula of your best fit line. Given any concentration, you can figure out the absorbance and vice versa. That's why it's called a calibration curve. Okay, or instead of using your calibration curve, if you know your other variables, you can also plug back into Beer's law. You know the absorbance, you can figure out the concentration, or vice versa. Okay, other things to make sure of in the lab is, like here, there must be enough sample in the tube to make sure that the entire light path is covered. So a lot of times we made sure that the test tubes were filled up at least, 3/4 of the way or so like that. If you don't have enough solution in there, the light might be passing through an empty test tube rather than the solution. You also want to make sure that you periodically, that you've used a standard. You want to make sure that you've calibrated your machine, as we said before. The solutions do not have to be saturated. They can be unsaturated. They can be concentrated or dilute. It's you're figuring out the concentration based on the absorbance.